about 5 minutes. 6 minutes already, I'm sorry. I will speak on the major open questions on the definability of the DC and degree classes in broader degree classes, for instance, computably enumerable degrees and some other degrees in the full degree structure and so on. First, I will consider only degrees which are situated below the jump. I mean Turing degrees of observability. Situated below the jump, the degree of halting problem. The main ingredient of this degree is computably enumerable degrees, and considering finite Boolean combinations of these degrees, we obtain broader and broader classes. For instance, differences of computably enumerable degrees and sets degrees of differences of computably enumerable sets and finite Boolean combinations of computably enumerable sets. Yershov, in his paper from 1968, extended this hierarchy to the using constructive ordinals to the other classes, sorting the covering all degrees situated below the jump. Here, the necessary pictures. Here, if we will consider the full degrees below the jump, then least one is computably enumerable degrees, degrees which contain computably enumerable sets, and then broader class DC degrees, degrees which contain differences of computably enumerable sets, and so on. Finite Boolean combinations, and extending by constructing ordinals, we will cover all degrees below the jump. We will consider only one open question, definability of these classes in broader classes of degrees. There are two possibilities to consider such questions. First, definability of degrees in the language of sets. In the language of sets, if you will consider the lattice of computably enumerable sets or partial E1, En means the partial ordered by inclusion class of NC sets, and E infinite means the union of all NC sets. We will consider the language inclusion, and the operations cap and cap operations are partial defined in the structures, except at sigma 1 and E infinite. E infinite is a Boolean algebra. Sigma 1 is lattice. Sigma 2 is, it is known that lower semi-lattice. All others partial ordered sets. We will consider definability of degrees, degree classes in these languages. For instance, we say that class of degrees definable in En if there exists definable class of sets from this class, such that our class of degrees exactly degrees of this sets. For example, the class zero degree of computable set is definable because it's the degree of the empty set. It is a first possibility to study definability questions. Second possibility, we will consider degrees, again, classes degrees below the jump and NC degrees. And the language, Turing reducibility, partial ordered classes of sets in this language, and definability of classes in this language, which means that there exists a formula, a class of degrees, definable if for some formula. This formula exactly defines in this class, this class of degrees, in this structure, this class of degrees. We will consider both directions, but in the first direction, only carefully study the case when the case of computably enumerable sets. Definability of jump classes, so-called jump classes in the computably enumerable sets in the language. Here, the definition of these jump classes, Hn, it is n high degrees, n nth jump of the A coincides with n plus 1 jump of Z. And low, class of low degrees, it is the class of degrees, the n jump coincides with the n jump of Z. NP set. Definability of these classes studied, and here, first for the case of computably high degree only, when n equal to 1, the old result of Martin, which characterized high degrees using so-called maximal sets, defines high degrees in the language of computably enumerable sets. And also, for all other classes, the result is obtained. First, it is proved that for some of these classes upper closed, for instance, high classes, n high classes, they are upper closed. All of them definable. It is proved by definable upper closed classes high degrees and complementers of low degrees. All of them definable except L1, complement of L1. It was a long time of an open question. And low closed classes, they are low degrees and complementers of high degrees. Low closed means if A is low, for instance, so any degree B below A also low. And so for other low closed classes. All of them undefinable. It was proved by persons who listed here, and a single theorem which helps to prove this result, constructing a low so-called promptly simple set, computably enumerable, which is automorphic to a complete set, and it follows all non-definability results. The case when L1 remained open until last years when surprisingly Epstein proved that it is undefinable. This is single class, non-low degrees which are not definable, and upper closed. All other upper closed classes are definable. If we will consider the case when n above 0, above 1, in this setting, these questions are never considered before. Only few results I will list now. For instance, first, it's very easy to see by this theorem that all computable sets are definable by this formula in all NC sets. And there is a theorem, Lemp and Lees, recently I knew about, that the class of computably enumerable sets is definable in the class of 2 CE sets, in the class of differences of computably enumerable sets. It follows from here as a corollary the class of computably enumerable degrees are definable in the class of computably enumerable degrees definable in the class of DCE sets in this edge. They proved that a computably enumerable set is DCE set is computably enumerable if and only if it is a supremum of two DCE sets with a unique complement. Recently, I proved that for each n, computably enumerable sets are definable in NCE sets. I didn't include it here because this result was just obtained, but for instance, it's interesting to compare it with the theorem of Nielsen Lemp. Here, another definition of computably enumerable sets in the language DCE sets. For the case n equal to, the following is true. A set A computably enumerable in DCE sets. DCE means that difference of two computably enumerable sets. Computably enumerable if and only if A is disjoint union of two computably enumerable sets such that for each of them, for each I below or equal by AI, for any x, if AI subset of x, then there exists as y I such that yi is x minus I. AI. So this sentence different from the sentence which was found by Limp and Nies, and also by a more complicated argumentation, this result can be extended to all levels of the hierarchy, finite levels of the hierarchy. It is interesting because if we prove definability of computably enumerable sets in all levels of the finite hierarchy, finite issue hierarchy, this will mean that all MCE sets are definable in NCE sets for M below N, because MCE set is a Boolean combination of computably enumerable sets. And this will mean also that the class of MCE degrees are definable in the language of NCE sets. It is a good result, completely different from the second approach of investigation via the language of Turing reducibility. I will speak about later. Now, if we will consider the we will consider now other classes of degrees. For instance, before, preceding results show that the whole classes of NCE sets, computably enumerable sets, definable and undefinable in the broader classes of degrees. But if we will consider proper classes, for instance, jump classes, again, it's interesting to extend results of obtained for computably enumerable case. Here, only the following result is true. The class of computably enumerable high degrees definable in En for even n. The proof is outlined in the sketch of the proof. First, we need to show that cohesive means infinite set is cohesive if it cannot be split by computably enumerable sets to infinite parts. NCE cohesive sets are definable in NCE sets for each n, and any NCE cohesive set is co-computably enumerable. It is a generalization of famous Lachlan theorem on hyper-Riemann sets, and then this is true. It follows from the first two parts that the class of high computably enumerable degrees coincide with the degrees of NCE cohesive sets. This is only a result about definability of jump classes in the broader structures. But the following theorem, can be obtained analyzing and generalization the previous argumentation for each level of the hierarchy. First, it is necessary to note that in NCE degree hierarchy, there are not only high computably enumerable degrees. The following theorem is true. For any n, for any fixed n, there exists NCE, properly NCE, a high degree. Properly means it belongs to this level, but not lower levels of the hierarchy. And we can found a definable set of degrees which contain high degrees from this class, which is definable in this class. This is only results in this direction. And the following theorem shows that the structure is quite complicated from the computability point of view. Each of them does not contain computable presentations, computable copies. And now let me turn to the second part of our consideration when we will consider definability in the language of Turing reducibility. Here, there was only one known result. All results, all questions are open, and decision process is very hard. Only one, there was only one definable set of computably enumerable degrees definable in the structure of DCE degrees. This is by joint work of myself, Iskander Kalimulin, and Stephen Lem, which states that this formula defines the infinite set of computably enumerable degrees. Recently, with Yamaleyev, we found another promising set. We know a few words I will say about it. Part A proved by Yamaleyev, part B proved by myself. Yamaleyev proved that if we will take properly DCE degree, properly DCE means it contains difference of two computably enumerable sets, but not computably enumerable. Doesn't contain. It can be each splitting into DCE degrees have two parts. At least one of its parts have the following property: each DCE degree is splittable avoiding the lower cone. Lower cone means that splitting does not above, each part of the splitting does not above a lower degree. And the second part states that there exists this computably enumerable set. So it cannot be by the part A DCE computably enumerable degree, which can be split into two DCE degrees, so that each part contains a DCE degree, which cannot be split by this way. So we have a non-trivial definition of computably enumerable degrees. And main open question here, low density conjecture. We assume that for each low degrees, for each pair of comparable low degrees A below B, there exists a degree below this definable set. Between each pair of low DCE degrees, CE degrees, there exists a degree from this part. It follows, it gives definability. If the conjecture is true, it gives a definability of computably enumerable, the solution of the problem, because of Sachs theorem. Sachs proves that each computably enumerable degree can be split into two low computably enumerable degrees. Then, using this theorem and low density conjecture, we can solve this problem. First, we split any given computably enumerable degree using Sachs splitting theorem into two CE degrees. After that, for each above each of them, find another low degree. Between them, find definable degree from the low density conjecture, which union gives our degree. But unfortunately, we cannot prove this low density conjecture. The only theorem which can be proved using the proof of the original theorem plus high permitting method. Below any high computably enumerable degree, we can find such a degree. The question is that, can we change here highness by lowness? But it is, there is no idea here to solve this question also. So this question remains unfortunately open. Now, if we will consider, definability using parameters, then for any given low NCE degree, the following theorem is true. It can be proved using Slaman and Woodin's characterization, such kind of results. I will see we will say about. For any given NCE low degree, the class of all degrees below it, definable using parameters. It follows from this technical theorem, definition of the low set given here, and Slaman-Woodin's theorem, which remain. If we will add here, and the open questions here, all remaining questions are open. Most interesting question, of course, definability of computably enumerable degrees in the delta 2 degrees, in the degrees of below the jump, definability NCE degrees in the broader classes of degrees, And also it is interesting to consider if we will add to our language additional parameters. But for instance, only easy case, when if we will add this new relation, computably enumerable in and above, then immediately we have definability of computably enumerable degrees by this formula. And using my old jointly obtained with Slaman and Lafort result, we can obtain definability of DCE degrees and the broader classes. It is open question again, can we extend this result changing DCE to 3CE and so on. And also it's very interesting question, of course, here, which kind of relations we can add to our language to obtain definability of several classes. And this approach can be considered as an attempt to solution of the main open problem about definability without parameters. And again, the following theorem shows that these degree structures, again, quite complicated. Thank you very much.
Are there any questions? Questions? What kind of reducibility did you consider? Because when you are below the first Turing jump, there might be some issues about.
We considered here only Turing reducibility,
yes,
reducible Turing, and nothing more. But of course, it's interesting to consider also other vector stable when questions to Oracle limited by a computable function. And for instance, Klaus Amberspies studies the Turing reducibility when strictly questions we can ask about strictly below x, for instance, or below some polynomial. It's interesting, but for Turing reducibility, it's very difficult. I think for others, it's more complicated. Nothing is known. Maybe Rod knows more, I don't know, because he, for a while ago, studied these questions. I mentioned his name here in my talk.
Okay. Thank you very much. Then.